You have to find the formula from a percent or from grams. And the formulas that we're talking about, those subscripts we're speaking of, are actually internal mole ratios. Internal mole ratios means that those quantities that are given to you must be converted to moles before you can actually get the ratio. So generally, and if you want to just take a picture of this, or maybe you remember this from Honors 10, that's fine. But whenever you're given questions within reason, okay, generally you're going to be given either percent composition of a compound or grams of that composition of the compound. So if you are given a percent composition of a compound, that means that you are generally going to have to assume that you have a 100-gram sample. And assuming you have a 100-gram sample, it's really easy to take that sample and convert the sample to grams. And I'll do an example of this momentarily. After you assume your sample is grams and you have grams, you can take those grams and you convert them to moles using its molar mass of the element. First step is always get to moles. However you got to get to it, get to moles. After you get the moles of all the components of a compound, you then have to compare the moles. What I mean by compare is you're getting the smallest ratio. Well, the way you get the smallest ratio is to divide by the number of moles, the smallest number of moles, to get the smallest ratio. An example will mean more to you than this probably does right now. At the end, is let's say you divide and you get, 2.5. Well, you know you can't put 2.5 as a subscript, so you must find a way to get to full integers. Let's say you have a 0.5 number. That means just to get to a full number, you need to multiply all the subscripts by 2. If you have a 0.33 or 0.67 ending, you multiply all the numbers by 3, and so forth. So the reason you do all of them is because they all have to remain in the same ratio. You can't just do the single subscript that doesn't meet the integer qualification. You have to do them all. So I want to show you an example first. And the example is in your packet. Let me find my packet. I have a packet. It is student example 1, sample of unknown compound mass, and I'll show you on the board. I just want to leave that there in case people were writing down the multipliers here. Okay, so sample of an unknown compound with a mass of 2.571 grams was analyzed and found to contain that much carbon and that much oxygen. What are the two components of the compound? What are the two components? Carbon and oxygen. So this one is actually given to you in grams, not in percent, which makes it a little easier. You have that first step's already been accomplished for you. So what you do is first convert to what? Moles. So 1.102 grams of carbon is one sample. 1.469 grams of oxygen is the other sample, or the other component of the sample. Together, that's 2.571, and you could also be only given the total mass in one of the compounds or one of the elements, and find the other one just simply through subtraction. But this gives you both. So first step. Calculator dead. Ooh. Okay, so carbon, you're converting to moles, right? 1 mole of carbon, and oxygen you're converting to moles. Carbon is 12.01 grams, which is a smaller mass. Oxygen is 16.00. Where am I getting these numbers from? Grab table. And I'm giving you the calculated versions just so you have a sample in front of you for each of these. But this first one gives you 0.09175 moles. The second one gives you 0.09181 moles. I'm videoing too, so if you want to rewatch, it's cool. But comparatively, you can definitely tell the ratio. Approximately what, guys? 1 to 1. For every 0.09 of these, you got 0.09 of these. It's a 1 to 1 ratio. But to solidify that, that's where you divide by the lowest number. Well, the lowest number happens to be this one. So when I take the moles that I got, divided by the lowest moles achieved, you divide them both by the lowest number. This is definitely 1 because you're dividing it by itself. This is approximately 1. And when you plug in your calculator, it's like 1.01-ish. So I'm rounding that to 1. It's roundable because it's not too significantly far away from the whole integer. So that one's easy. The ratio is 1 to 1. Carbon 1, oxygen 1, which is, it looks stupid to write the 1, so we just write CO. So that is carbon what? Monoxide. All right, cool. So this empirical formula is already is already kind of embedded based on the ratio we achieved here. No need to multiply at all. Thumbs up if that empirical formula makes sense. You remember the steps. First step, what? Convert to moles. Second step, divide by lowest. Third step, multiply if needed, or take these as the subscripts. That's your process every single time. All right, so this one does not start you off in grams, okay? This starts you as percents. So you're going to assume a 100 gram sample, which is easy. If I have 100 gram sample, that means I have how much barium? 69.58 grams of barium and 6.090 grams of carbon and 24.32 grams of oxygen. That's all that percent takes us to, is just a gram, and then we're again going to go step by step like we just did, convert to moles, and then compare moles. And I'm showing you the sample. It's exactly the same set of steps though. 1 mole of barium, carbon, and oxygen. Molar mass of barium is 79. Nope, lies. 137. I'm thinking bromine. 137.33 grams. Carbon is 12.01 grams, and oxygen is 16 grams. And upon calculation, you get barium to be 0.5067 moles. You get carbon to be 0.5070 moles, and oxygen to be 1.52 moles. So this one happens to be one where you do need to, again, divide by the lowest number. And which one are we dividing by? The top. So that divided by itself is 1, right? That divided, in these little ditto marks, I'm just putting ditto for now. That divided by itself is 1. This divided by approximately, it's, you know, a very, very close number. Again, it's going to be 1, and this one will be approximately 3. And it's like 3.01 or something like that too, so it's roundable. So these are subscripts. What's the compound? Barium carbonate, BaCO3. All right, that's empirical formula. Yeah.
What would you consider significantly away from the whole integer?
So it's only roundable if it is, so like if it's 0.85 and up, you can round up. And if it's 0.15 and down, it's rounded down. Usually the stuff in the middle, like 0.2, you're going to multiply by, if you multiply 0.2 by 5, you get a whole integer. But if you have a chance to reduce the end, you will reduce. Okay. All right, so if you have something that does not ask for empirical, it asks for molecular, there's just a slight difference. It's not the most reduced version. So in this case, you're going to have a multiplier across all the subscripts that make it not as reduced as it should be. So a lot of times our covalent compounds, so molecular again means covalent generally, those are not going to always be 100% reduced. The reason, or the way you would figure out the integer that you're multiplying all the subscripts by, are to have the molecular mass and the empirical formula mass to compare. So a lot of times, I'll show you an example. Well, I can show you here too. So if you're given a molecular mass of 250 grams per mole, that's the whole shebang, that's the whole sample. And whenever you have the empirical formula, and you count up the subscripts and you find the molar mass, you find that's only 125, what that means is that this needs to be multiplied by 2 to make it to the total mass of the sample. So let's say I had, I'm just going to make up one for now, guys, C2H5. Let's say that was my empirical, because you can see it's not going to be reduced anymore. And I found that the molar mass truly was double. What I would do is I would need to multiply all the subscripts by 2, because the molar mass needs to be doubled, so that would be C4H10. You need to multiply each of these. I'm going to show you a sample though. Alrighty. Here we have an oxide of phosphorus, gives us our percent, and it doesn't tell us oxygen, but we can figure it out, right? out of 100, and it says the molecular weight is 284. First thing first, we cannot find the molecular until we have the empirical formula. So let's find the empirical. And I'll try to give you the math up here too. So that right there is going to be 43.7 grams of phosphorus. How much oxygen? So you're just taking 100 minus 43.7, 56.3 grams of oxygen. Oh, the molar mass. So we're, again, took our percent to grams. Grams to moles. 1 mole of phosphorus. 1 mole of oxygen. This is 30.97. 16 again. Okay, so when you divide, you get 1.411 moles and 3.52 moles. So you can probably show me a quick division, or you might be able to divide in your head. Tell me when you divide this by itself, I know you can get 1. What happens when you divide this? 2.5. So now we have our first non-full integer, correct? So then what do we need to do? Multiply which one by 2? Oh, good. So since this is 2.5, you can't keep that. You got to multiply it by 2, as well as this one, because they need to remain the same ratio. So what's the empirical formula? P2O5. Name it. Diphosphorus pentoxide. Good. Right, so that's the empirical formula. What's the molar mass? Can you give me a quick calculation? Even an estimate is fine. Phosphorus weighs about 31. 2 phosphori? 62 plus 16 times 5? 141. Was that what you said? All right, so this is approximately 141 grams per mole. And that's the empirical formula mass, right? 141. The molecular mass is 248. What's my multiplier? 2. So what you're looking at is the difference, the multiplier difference between 141 and 248. So in your head, you're doing 248 divided by 141 grams per mole, grams per mole. And when you did that, you got 2. So what is the molecular formula? Okay, so you're putting 2 there, right? So P4O10, name it. Tetraphosphorus decoxide. You can say deca-oxide or just decoxide, that's fine too. So not much more, except that final comparison between empirical and molecular mass. Do you see how it's really similar, it's just one extra step? All right, so this was all previous knowledge, okay? All of this is previous knowledge. No one knows what combustion analysis is. But you can imagine it deals with what kind of reactions? Oh, nice, okay. So, combustion analysis does have to deal with reactions that are having a hydrocarbon or a hydrocarbon with oxygen in it react with O2 oxygen. This is new for everybody, okay? So this is at least write down the first 2 examples with me. I'm only going to do 2. I'm going to do one with just a plain old hydrocarbon and one with oxygen-containing hydrocarbon. Okay, so why would we want to do this? Let's say some arsonist is catching something on fire, right? There's a residue remaining, and we can't figure out what it is. We know it's some sort of fuel that they've used, some hydrocarbon they've used, and we want to analyze it. Well, just in case, we've got some analytical chemists, and they're capturing, as the building is burning, they're capturing the carbon dioxide and water that's coming off this reaction, because every single combustion reaction has carbon dioxide and water coming off. They collected all the all the carbon dioxide and all the water, and they have it. Where did the carbon come from? Where did the carbon from the carbon dioxide come from? The hydrocarbon, right? Where did the hydrogen from the hydrocarbon come from? The hydrocarbon. If they can analyze what's in here, they can figure out the unknown formula of the fuels and backtrack it to the arsonist, right? Okay, so there is some real impact here. And then also same way here. Basically, all that carbon came from the hydrocarbon, all of that hydrogen came from the hydrocarbon. So we're really analyzing the products, to figure out the reactants. So that's what we're going to start with. And it's the same process of empirical formula, except there's one tail end that's a little different. So Let's move. Can I move? Yeah. Okay. So this is a diagram of how you can do them in the lab. They have something this is called a tube. U-tubes can collect water or vapors, and one that can collect carbon dioxide, and they can actually weigh it, figure out the grams of the carbon dioxide in water evolve, and then they can analyze from that. So there is a lot in the lab that can be done with this as well. Okay, this is your step-by-step process. I like to give you the steps so we can repeat them as we go. Picture or write down with me as we go. But generally, whenever you're given a problem like this, you'll be given the grams of the two products, carbon dioxide and water. We all know grams are useless to us. We generally will need to go to moles. And I'm talking about both these at the same time. Well, once we're to moles of carbon dioxide and water, that's only useful because then we can whittle down to just the carbon and just the hydrogen. Whittling it down to just analyze the single parts we need. And then I got this last step to go to grams. We will use these. You don't have to go all the way to grams first, but I only highlight these in red because I want you to know that when we do have to go from moles back to grams of carbon and back to grams of hydrogen, notice that this hydrogen is not diatomic hydrogen. Why is this not diatomic hydrogen? What are we comparing this to? Where did this hydrogen come from? The hydrocarbon. And that's within a compound, right? You never put diatomics unless they're all by them or low lonesome in a reaction. This is the hydrogen from the compound, which is not diatomic. It's within a compound. So these two we're going to look at later, because if the hydrocarbon, and you only do this if the hydrocarbon contains oxygen, okay, you will look at these, you'll compare it to the oxygen, or compare it to the mass of the original hydrocarbon, and you'll utilize that to find the oxygen. But I'm going to get there after we do the easy example first. This I found is the easiest method. There's another method that's a little bit more elaborate. It also works. So don't think there's my way or the highway. There are other ways to solve, okay? So I'll come back to this as we review the oxygen-containing one. Lovely. I'm moving on to an example. Okay. This is on your paper. Do you see it? I think it's on the next page where it says combustion analysis. Oh, look, I get to do the combustion formulas and everything. Okay. Do you see it? Do we need this right now? Yes, yours? All right, so first example, compound contains only carbon and hydrogen. Yes, not an oxygen containing one. All right, so that's helpful. We have this reaction, CXY plus oxygen yields carbon dioxide and water. And I just like to write the reaction down so we can label the parts as we go. A 1.45 gram sample, okay, so that's our sample. I need this calligraphy pen because it makes me write better, okay? So 1.45 grams is my original sample. You got me? You with me? Okay. Produces 2.25 grams of water and 4.40 grams of carbon dioxide. Determine the empirical formula for the hydrocarbon. If I wanted you to, and sometimes I will, using the law of conservation of mass or matter, how much oxygen was burned? What would you do? Okay, so you'd find the oxygen. So you would do this, what is this? 6.65? 6.65 minus 1.45? 4.10? I think that's right. Okay. So I could ask you how much oxygen, free oxygen was burned. I could add that to the question. I didn't hear, but I wanted you to know you could do it due to the law of conservation of matter. Okay, so with our empirical formula, very first thing we did was take our back to the combustion analysis example steps. We took our carbon dioxide grams and we converted it to moles, right? So we took our mole of carbon dioxide, that's 44.01 grams. Okay, and then nobody cares about carbon dioxide. What do we want out of it? The carbon. How many carbons are in a carbon dioxide? 1. So yes, write it, okay? 1 mole of carbon internally for every 1 mole of carbon dioxide. That's our internal mole ratio. Okay, I'm gonna stop there. Don't go to grams on this one. Stop here. That is 0.1 something. 0.1. Oh, sorry, 0.09999773 moles of carbon. All right, did I go too fast? Is that okay? All right, so we're doing the same thing for now what? Water. Okay, so water starts off with what? 2.25 grams of water. 1 mole of water. See how I'm labeling everything? I'm modeling it for you so that in your lab notebooks you know to label your carbon dioxide, and you're like, oh, what is this carbon? Now I got water, 18.02 or 18.016, but I got 18.02 in my paper and I have the calculations for you, so work with me here. We got our water. Now what am I going to? Okay, what's that internal mole ratio? 2, right, 2 hydrogens, and that's moles of just H, not H2. 2 moles of hydrogen for every 1 mole of water. Okay. What is this? 0.2497. Okay. Now, this is where it gets familiar. Now we're to just single atoms. If they're in their moles, how do I get an empirical formula from this? Divide by the smallest one and just figure out the ratio, right? Alright, so I'm dividing by this one, right? 0.0999 blah blah blah. That's 1. Alright, and then divide this by 0.0999 blah blah blah. And that's like what? 2.5. Okay? So here's our 2.5 again. That's a 1. What's the empirical form? Or what do we need to do to that? Multiply by 2. What's the empirical formula? C2H5. That's the wretched fuel that burned down the house or something. Okay? Notice we didn't even touch the oxygen. No need to, because we dissected the two products so well. Who cares about the oxygen? It doesn't matter. We have exactly the carbon hydrogen that we've had from the fuel, and then we convert it to appropriate the lowest ratio for the empirical formula. Not too new, right? Not too crazy. Now, the next one, a little bit more, okay? I have 15 minutes, so we're going to finish this one too. All right, so I want you to do what I did first with you. What was the very first thing I did? I read the BCE and all the givens. Okay, so 5 grams of an oxygen-containing hydrocarbon, which means CXHYOZ. Okay, that's just the abbreviation. It's 5 grams. It must yield 9.57 grams of carbon dioxide and 5.87 grams of water. And I could ask for how much oxygen additional was there, but I'm not right now. All right, so let's start with the exact same. You guys work with me, but I'm going to write down the calculations just so you don't have to. So we're starting with, I always start with carbon dioxide. If you stick with the same way all the time, you won't forget it, because it will be burned into your brain. So I converted the moles of carbon dioxide. Now I'm dissecting further to just carbon, and I know that we could probably find a way to skip a step. Once you're really good, you can. Nick Owen used to, and you'll get on my nerves because he would do everything about half the amount of steps that I did, but I like to model it all out, just for you. Okay, so actually I'm going to stop here for a second. Here's our moles, because then after this, after our moles, we're going to then convert to grams, but you need your moles, so I don't want you to neglect calculating them. So that is 0.21745 moles of carbon. All right, same story for our water. 5.87 grams of water. 1 mole of water is 18.02 grams. And then there's 2 moles of hydrogen in that single mole of water. That is 0.651 moles of hydrogen. Okay. So there we're sitting comfortable, right? What was different about the oxygen containing ones in the instructions? From what? From the total hydrocarbon. Okay. So we have our moles of carbon and moles of hydrogen. We are going to convert this to grams and this to grams. And that's going to add up to be less than 5 because the total mass of the hydrocarbon is 5. So if we can subtract the mass from this, we're going to get just simply grams of oxygen, right? Then what do you think we're going to do with that? Convert to moles, so then we can compare our moles, moles, and moles of oxygen, and again, do the empirical formula. That's the only extra step, okay? So, let's convert. I'm just going to take that, and that's 1 mole of carbon is 12.01, and that is, thank you, I hear you, 2 point what? 1. I'm going to go just a little farther, just in case. And then this for hydrogen, 1 mole of hydrogen is 1.008. Whoa, you see that? Okay, hydrogen, and that gives me 0.6567 grams of hydrogen. Circling and squaring off and labeling, whatever you gotta do so you don't miss where your work is. Okay, and when we add that up between the two components we do know, that is, I didn't add it up, I just subtracted twice, but there we go, 5 grams total, minus the grams of carbon, minus the grams of hydrogen, is 1.7318 grams of oxygen. Again, it's just single, it's not diatomic because it's within a compound. And then what did you guys say to do this? Convert to moles. It's not a hard process, just a long process. And that would give you 1.08 moles of oxygen. Noticing I'm even labeling which moles is talking about who is what so that you don't get lost in your work. That's not 1.08. What is that?
Yeah, for the moles, I got 0.108.
Oh, I fixed it. I've written on top of those twice. 0.108. Yeah, that doesn't make sense. I saw Levi's face. So like, oh, that's not right. 0.108. There you go. Okay, so then what are you going to do? Okay, so who's the smallest moles? Oxygens. So divide each of these by 0.08 or 0.108. This is going to be on the very bottom. This one's going to be 1, because you're dividing by itself. This one is going to be 6.
6.02.
What is it, 6.02? So I can round to 6. Okay. So this one is 6 for hydrogen, and then carbon should be 2, right? Is there? There's no hanging decimal. Okay. I didn't fix that, so I'm not looking at that anymore. So I'm guessing that when you divide this, is going to be just 2. Okay. What is the empirical formula? C2H6O1. Okay. Okay. So I walked through that really fast because I wanted to make sure you had at least one example of each, even if it's just on video, you watched versus right. I'm cool with that. But I also want to see how many we actually need to do for homework. I don't think we need to do them all for homework. Can I see that paperback real fast, AJ?
Yeah.
All right, you look at the problem set on the next side. I gotta write down what I'm assigning to you so that I remember to put this on the website. Well, hold on, before I move on. 1 out of 10. Don't lie. You're awesome, like you got the process. 1, what the heck had just happened? Like use your fingers. Okay, so, but you could refer back to the process and help yourself along. Yes? Okay. So I want you to do, since I have the answers for the first ones, you can check yourself as you go. 5, because that one has CH and O in it. 4, because it has molecular formula in it. And do all these have oxygen too? And 1 on the following more combustion analysis. So you got 4, 5, and 1. Okay? You need to borrow this?
Yeah.
4, 5, and 1. Alright, so circle those. If you need to put your data on the board, you want to put it back up here? We have about 8 minutes or 6 minutes left. You could probably knock out one of those combustion analysis problems if you want to. Or put data. Who's ready to put data up here? Your group is? Okay. Because you need to write down other people's data. You need to have this little, I mean, I'll type this up for you, but you need to have it.
I can do this.
Don't do nothing. Oh, does anybody have money? Jacob, I have a 20 and $2. Alright, I don't have it. Oh, no, hold
I'll
on.
have it.
Hold on. Nope. I have $9.
I mean, I'll
I'll give you $1 back later.
That's fine, yeah.
What do you need?
I just need a 9, and I'll give you 30.
Oh, okay. But I can't. You have what?
$10
You
bill.
need, yeah. Oh, let me just open it, because I can't use my money because they replace it. I don't think I can use
I mean, I can give you 25, and you can give me 4. So if I give you 30, you can give me 4 back. Does that make sense?
So that's from me, from school.
Oh,
You
I
need it
got
back
you.
from school. I can give you 5 back next week. Or wait.
For this circuit work, that's week, yeah, that's fine. So I will forget about it.
Do not pack up yet. You have 5 minutes left. Do not pack up. Heck no. Do not pack up early. You have data to write down, or you have combustion analysis problems to do. But if at all possible, if anybody wants to work on this, then I need data. So it doesn't look like anybody's going to write data, so I'm going to leave this. What are you doing? Crazy. Okay.